Alrighty, welcome back, everyone. Today we're going to be looking at graphing and vectors in 3 dimensions. So this is going to be super fun and kind of mind-blowing. But these are called ordered triples, not ordered pairs, because we have an x, y, and a z axis. So to graph ordered triples, graphing a point in 3 dimensions, first you have to know what each axis is. So we're used to having 2 axes, our x-axis and our y-axis. Okay, so we still have an x and a y-axis over here, except just picture it as if it's laying flat, like on a desk. So this is going to be our x-axis, right here, and this is our y-axis. So picture that laying flat on the desk in 3 dimensions. And then our z-axis is actually the vertical axis. So this is how far it goes up. So this would be if you took your grid on your desk and you lifted it up in the air. That would be your z-axis, how tall it is, or how high it's lifting up. Okay, so we have an x, y, and a z-axis. So if you're given an ordered triple, it's written in the form x, comma, y, comma, z. So for example, if we have the point 3, negative 5, and 7. This tells us we are at 3 on the x-axis, negative 5 on the y, and then 7 on the z-axis. Okay, so this is going to be our positive x-axis. This is the negative x-axis. This is the positive y-axis. This is the negative y-axis. Then positive z, negative z. Alright, so 3, negative 5, 7. So the first is to find the distance on the x-axis. So it was 3 if we're using that point. So that would be positive 3, so right here. Then find the distance on the y-axis. So that was negative 5, I think. 3, negative 5, 7. Just write that down. 3, negative 5, 7. Okay. So negative 5 on the y-axis would be 1, 2, 3, 4, 5, about here. Okay, so we have our 3 on the x, negative 5 on the y. That's not the actual points, but we're going to use those. That's where they would, that's where we're basing it off of. Okay, next is going to be, up here on the top, is to draw dotted lines parallel to the x and the y axis. So for example, we know that the x is at 3, so that's here. I'm going to draw a parallel line, a dotted parallel line to my y-axis. So like this, it's parallel to the y-axis. Don't worry about where it crosses that z-axis, because really it's just imaginary right now. This is lying flat, so it's not actually crossing the z-axis. And then our y was at negative 5, 1, 2, 3, 4, 5. So I'm going to draw that parallel to the x-axis. So kind of like this. Okay, and where those cross right here, that would be our xy point. So if we're just doing 2 dimensions, x comma y, that's where it would be. Okay. Then we have to do the z distance. So our z distance was 7. 1, 2, 3, 4, 5, 6, 7, very top up here. Okay, so that means that's how tall we're going to bring this point up. That's how high it's going to come up. So now we basically just connect all those. So let me redraw it down here. So we have our x, which was a negative 3, our y at negative 5, 1, 2, 3, 4, 5. So it's crossing the y-axis at negative 5. And then our z was up here at 1, 2, 3, 4, 5, 6, 7. So that's going to be up to here. So we're going to take this point and we're going to raise it up to negative 7. So it should cross here. And that should be your new point. So negative 3 on the x. Negative 5 on the y. Then you're raising that up 7. So that is our point 3, negative 5, 7. Okay, so that point, we found the 3, negative 5, and then we just brought it up straight up vertically 7 units, essentially is what we did. Okay, you can do that with any three-dimensional point. Okay, if it was -7, we would just start here again and we would go down 7, so it would be like this. We put it here. Okay, all right, on to the next one. Okay, so this is talking about vectors. How do you find the ordered triple that represents the vector p1, p2 when the initial point is x1, y1, z1 and the terminal point x2, y2, z2? So it's actually just very similar to what we did with 2 dimensions. So we'd write our vector p1, p2, and it would be, you just subtract them, so x2 minus x1. You're finding the distance of your x's basically. y2 minus y1, z2 minus z1. Okay, so for example, if we have our point x at, maybe I shouldn't use x, so well, 5, -3, 2, and point y at 4, -5, 6. To find our vector xy, so it starts at x, goes to y, we're going to do 5 minus 4, which is 1, -3 minus -5, which is -3 plus 5 is 2, and then 2 minus 6 is -4. So it goes 1 unit, it's 1 unit in the x direction, 2 units in the y direction, -4 units in the z direction. Okay, how do we find the magnitude of a three-dimensional vector? Well, again, magnitude is just like the distance formula. So if we have these 2 points, p1 and p2, to find the distance between those, remember that's what we use for magnitude. We just use the distance formula, but we do it for 3 dimensions. So x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So it's essentially the same thing, you're just adding that third component. So again, if we have our points 5, -3, 2, and y, which was 4, -5, 6, we would just do to find the magnitude of xy. We would do square root 5 minus 4 squared plus -3 minus -5, which is -3, wait, -5 plus 3, I guess. You can do it either way, because it's squared anyway, so it doesn't matter. Plus 2 minus 6 squared. Okay, if you do all that, it should come out to be square root of 21. Okay, and actually, now that I'm thinking about it, that last one I did up here was not right. Sorry. I did x minus y. We need to do y minus x. So, because x is your initial point. Wow, okay. Y is your terminal point. So, the vector should actually be 4 minus 5, which is -1, -5 minus -3, which comes out to be -2, and then 6 minus 2, which is 4. Okay, so make sure you're doing this is our initial, this is the terminal. So make sure you're doing the terminal subtracted from the initial. Okay, so it just ended up changing your signs. Okay, the formulas are they're actually almost identically the same. You just have the third unit. So if we're adding a and b, this is our a vector, that's our b vector, we should just get a1 plus a2, no, sorry, a1 plus b1, you're adding the x's, a2 plus b2, because you're adding the y's, a3 plus b3, because you're adding the z's. Okay, subtraction, a1 minus b1, depending on which one is your, well, these are vectors, so I guess it doesn't matter. A2 minus b2, for your y's, a3 minus b3 for the z's. Scalar multiplication, that's when you're multiplying it by a number k. So it would be k times a1, a2, a3, or b1, b2, b3, whatever you want to do. But that just comes out to be, you just distribute it, ka1 for the x, ka2 for the y, ka3 for the z. Okay, and I'm not going to go over some examples because I feel like that's fairly simple and you should all be able to get that. Okay, next. Alright, so when you're finding the product of two vectors, we actually have two different products you could find. The first one is called the inner product, or more commonly known as the dot product. Okay, so if you have, these are just two-dimensional vectors, a and b. So to find the dot product, it's written like this, a dot b. Okay, so to find a dot b, you're basically just multiplying the x's together, the x values, so a1 times b1, plus your y values together, a2 times b2. Okay, if it is in 3 dimensions, same idea. So we do a dot b is a1 b1, so your x's, plus a2 b2 for the y's, plus a3 b3 for the z's. So for example, if we have our a as 5, 2, and our b vector is 4, 8, then to get our dot product, we do 5 times 4 plus 2 times 8. So that gives us 20 plus 16, which is 36. Okay, in 3 dimensions, if we have 5, 2, 1, so let's just add a 1 here, 5, 2, 1, and 4, 8, negative 7. Then we would just do 5 times 4, which is 20, plus 2 times 8, which is 16, plus 1 times negative 7, which is negative 7, and that should come out to be 29. So that would be a dot b. Okay, and your dot product is useful because it tells you if two vectors are perpendicular to each other. So if two vectors are perpendicular to each other, we call that normal. Those would be normal vectors. It's also called orthogonal. So normal, orthogonal. These just mean perpendicular. So if your dot product is 0, then those two vectors that you did the dot product of are actually orthogonal. They're normal vectors. They are perpendicular if the dot product is 0. Okay, and then the other product that we have is called the cross product. So we have to use the determinant of a 3 by 3 matrix to find the cross products of a vector in space. So we have, this is just a review of how to find the determinant of a 3 by 3. So basically, if we have our two vectors, a1, a2, a3, this is 3-dimensional, and b, which is b1, b2, b3, we're going to write it as a matrix, but on top, notice your top row, those are all the unit vectors I, j, and k. So you always do I, j, k on the top, and then you list your two vectors below that. So here and here are your two vectors. Okay, and then we find the cross product, or the determinant to find the cross product. So remember to find the determinant. So we're always going to use this row. You don't actually get to choose this time. You have to use the top row. So we're going to start with I, cross those out. So then we get I times the determinant that's left here. So A2, A3, B2, B3. And then to simplify that determinant, we just do the formula, multiply the diagonals, and subtract them. Okay, then to do J, circle this guy, cross these out. And remember, this is going to be negative because it's in the negative spot if we do your checkerboard. Okay, so we circle J. What is left? A1, A3, B1, B3. Find the determinant there. And then last, you do the K. Cross those out. We have A1, A1, A2, B1, B2, and then you subtract those. And this one's going to be a plus because it is in the positive spot there. Okay, so that is how we do the determinant. Okay, and then after you do that, that should actually give you your vector. Now a cross product tells you, it gives you, so you have two vectors, so let's say we have the vectors look like this and this. Say those are our two vectors. So the cross product will give you another vector that is perpendicular to both of these. So it would be, I guess if these are in a flat plane, the other vector would be coming straight up out of that plane. Or something like this, be going behind, like that. Okay, so it would be perpendicular to both of those, meaning this is three-dimensional. So it would be coming out of the plane formed by those two vectors. Okay, so let's look at an example here. Let's see. Does it give us an example? No, I think I have to write it. Okay, so let's use our first vector as, let's just say, 1, 3, 4 is our A vector, and then B is -1, 0, -1. Okay, so we're going to fill them in here. So our two vectors are 1, 3, 4, -1, 0, -1. Okay, so then we're going to list them here. I don't know why I have them in two spots, but 1, 3, 4, -1, 0, -1. Okay. I have it in three spots. Okay, well, fill it out for all of these, I guess. I'll pause this so we're not wasting time. Okay, now to get your I, we're going to circle the I, cross these out. So we're left with 3, 4, 0, -1. So that means we're going to do 3 times -1. These ones, minus 4 times 0, which is those ones. Okay, for J, we're going to circle the J, cross those out. We're left with 1, 4, -1, -1. So we're going to do 1 times -1, that's these ones. Subtract 4 times -1. And then K, cross those out. 1, 3, -1, 0. So 1 times 0 here. -1 times 3 there. Then we can go ahead and simplify. I just have it rewritten there. So basically we get -3 minus 0, so that's going to be -3i, because that's our I vector. Then this is minus plus. So here we get -1 minus -4, so plus 4. So we get, that's -3 times -j, so positive. No, that's positive 3 actually. That's going to be minus 3j. And then this one we get 0 minus 3, which is -3k. Wow, that's a lot of 3's. Okay, so this is actually the vector that is going to be perpendicular to these two vectors here and here. Okay, and we can rewrite this. This is in unit vector notation, so you can actually rewrite that as -3, -3, -3. So this vector right here is going to be perpendicular to both of those vectors. Okay, and yeah, that's pretty much it. Okay, that is all I have. That's vectors in 3 dimensions. Make sure you do the quiz, and I will catch y'all later.